Welcome to FXR Conversations. In this episode, we're talking about 556 ballistics with flash X-ray cinematography. This is all about using some really incredible X-ray technology to look inside materials during high-speed events, specifically seeing what happens when a bullet hits something.
That's right. Yeah, we're looking at some fascinating work here. It was done at the Military University of Technology in Warsaw. They're using flash X-ray, or FXR, equipment.
Okay.
And the system is pretty advanced. It's an SCF 454 channel MAT Cinematic FXR system.
Cinematic or Cine FXR. It sounds like you're making movies, but like with X-rays.
Exactly. Yeah, that's a good way to put it. The cinematic part means you can visualize, well, film-like motion.
Yeah.
But the key is you're seeing it happen inside stuff you can't normally see through.
Right. Opaque things.
Precisely. It uses a multi-anode tube, an MAT. Think of it as an X-ray source that can fire really, really quickly from different points, and a cinematic imaging detector.
Yeah.
Together, they capture a rapid sequence of these internal images.
So you get this burst of pictures showing the action unfolding where you couldn't see it otherwise.
Exactly. It enables something called fixed area time sequence imaging. You basically pick a spot you want to study, and the system snaps multiple images of that exact spot over incredibly short times, like microseconds apart.
Wow, microseconds.
Yeah. So this lets you analyze the process of something dynamic, like a bullet going through layers, actually as it happens in that one location.
That capability, that feels like a superpower, doesn't it? So what kind of experiment did they actually set up to show this off?
Well, they took a standard 5.56 round fired at a pretty high velocity, around 1,005 meters per second.
Okay.
And the target was this custom multi-layer structure. It was designed to kind of simulate different types of barriers.
What were the layers made of? What was in the stack?
Right. So they created this stack. First, a thin steel plate, only 0.3 millimeters. Then a slightly thicker one, 0.755 millimeters. After that, there was a layer of porous material with a density similar to wood. And then finally, a third steel structure made of two 0.75 millimeter plates.
Okay, so quite a challenging target then. How did the X-ray system capture all that as the bullet, ripped through?
They used a 300 keV flash X-ray source. That 300 keV, that tells you the energy of the X-rays. The output voltage is adjustable on scan-to-flash systems, and it was set just high enough to get through all those materials.
Makes sense.
And the setup geometry was pretty specific, too. The source was about 1 meter from the target, and the detector about a half meter behind it.
Okay.
Using that multi-anode tube we mentioned, it really helped minimize parallax distortion, so the images give you a clear, consistent view of what's happening.
Right, you don't want weird angles messing it up. And what did those images actually show? What was the sequence?
So they got 4 images, and they were captured just 16 microseconds apart. Really, really fast sequence. Yeah. And it vividly showed the bullet's journey. The first image caught it just as it was penetrating that initial thin steel plate.
Okay, image 1, hitting the first plate.
16 microseconds later, image 2 showed it traveling in the space between the first and second steel plates.
Still moving fast.
Oh, yeah. Image 3, another 16 microseconds on, captured it, penetrating the second thicker steel plate.
So it went through that one too. And the final moment, what did the fourth image show?
Well, in the fourth image, just 16 microseconds after hitting the second plate, the bullet's flight was basically stopped. It had gone through both steel plates and into the porous material.
Right.
But it was actually halted within that porous layer. It didn't make it to the final double-layer steel structure.
Wow. So you literally see the penetration, the flight between layers, the second penetration, and then the stop, all happening inside where you'd never normally see. What was the big takeaway from seeing that internal action?
Well, the main goal really was to watch how the bullet actually deforms during this whole complex penetration event.
The deformation.
Exactly. The researcher, Bartosz Fikus, he mentioned his students were particularly, struck by seeing the real deformation happening inside the layers.
Yeah.
Usually you can just see the entry hole, the exit hole, and the behavior of the bullet before and after perforation by using a high-speed camera. But that doesn't give us a visualization of the progression inside the target. And that's where flash X-ray can reveal some crucial phenomena of system behavior during each stage of the process.
Yeah.
It's a totally different level of understanding.
That must be incredibly valuable for teaching then. It's not just diagrams or theory. They're literally seeing the physics play out.
Absolutely. And they really highlighted the value for both education and research. The equipment, it's described as relatively easy to use, easy to sync up for experiments.
That helps.
And crucially, it seems quite cost-effective for frequent use. Parts like the X-ray tube anodes and cathodes, they can be easily swapped out.
Oh, interesting.
Yeah, so it allows for lots of student practice, lots of research exploration without, worrying too much about huge operating costs or wearing out super expensive components too quickly.
So you can run test after test, maybe try different materials or angles, and the students get really hands-on, like actually holding parts of the system, to really get how it works and how materials react under that kind of impact.
That seems to be a really key benefit, yes. It facilitates this practical, detailed study that, well, it might just be too expensive or difficult with other methods.
Okay, so for you, the listener, here's something to maybe chew on. How does seeing a dynamic, unseen process like that bullet deforming inside those layers fundamentally change your grasp of what's happening? Compared to just looking at the end result, the holes or the stopped bullet. It really makes you think about the forces and the material reactions in a completely different way, doesn't it?
It really does. Seeing the timeline, the actual interaction, it reveals the mechanics that are otherwise completely hidden. It definitely shifts your perspective from just static outcomes to the dynamic process itself.
If you've got a question about Flash X-ray cinematography, the team at ScandyFlash is ready to help. Just go to scandyflash.com and get in touch.
And if you want more tips about Flash X-ray, check out our other episodes of FXR Conversations, where we discuss all things related to Flash X-ray.